So, welcome back. I am with a new lecture in the series of lectures regarding magnetism and charges and currents, etc. And we are going to discuss what is written as Biot, S-A-V-A-R-T, Savart Law. But being French, their names are Biot-Savart Law. Okay. It gives us an idea to calculate the magnetic field due to a current element IDL. Okay. Here I have just shown XY as a wire which is carrying a current I from a positive polarity to a negative polarity. This is conventionally the current carried by positive charges. Okay. Now the DL element that we take, the length element, is in the sense of capital I. I'm not saying in the direction of capital I, because that makes capital I as a vector, which it is not. It is just charge per unit time, and charge and time, they are both scalars. So there is the DL element, and I have just taken a point P over here, okay, at a separation which is given by vector R. I am showing the vector R cap in the same direction. Okay. Now, all things clear to you, and then we find a dB over here, and this dB, the vector dB, which is the magnetic field due to the current element IDL, and that has been shown to be inside the board. Why? Because I've just shown that theta is the angle that this second vector R makes with the first vector DL. In fact, if you look at it, there is another angle that this R makes with this DL element, and that is this angle. Okay, this is less than 180 degrees as shown over here, and this one will be more than 180 degrees. So whenever there is a cross product, A cross B, A cross B, as I said that this is a new vector which is equal to C, say, and which is perpendicular to both this vector as well as this vector. Okay, just indicating. Okay, just like that, mentioning, because you are well versed with that by now. So let us say that if I rotate this vector, the first vector, towards the second vector through theta, where theta is the smaller of the two angles that the second vector makes with the first vector, second vector makes with the first vector. So here it turns out to be an clockwise angle, as we can see. Okay, and if I have a clockwise angle like that, and if I rotate my right hand, curl of the fingers from the first vector towards the second vector, then my thumb is pointing inside. So the direction of this dB will be into the board, and if you are drawing it on your copy, then into into your copy, into the paper. Okay. So far about this thing. This idea may have arrived from the Coulomb's law, where there was a charge Q and electric field was determined at a point away from it, but that electric field was either in the direction of this R if this were plus, or opposite to it if it were minus. But here there is a distinction that the magnetic field that we obtain is perpendicular to the plane containing dl and r, or dl or r cap. Okay. Now what are the things that we find? I'm not going to write this equation directly. We can see that the magnitude of the field dB is proportional to the current. Double the current and this will become double. Okay. Similarly, this is proportional to the magnitude of dl cross r cap. Okay. R cap of course is unity, so it is dl, so the element, if we take a larger element, then the dB will be more. If the element length is smaller, then the dB will be less. And the third thing is the beautiful inverse square law, that dB is proportional to 1 upon r square. So these three kinds of variables are there, and dB is proportional to all of them. Then I told you in many a case, in the case of Newton's law of universal gravitation, in the case of Coulomb's law, etc., that mathematical consistency says that dV will be proportional to the product of all these things, and dl cross r will be equal to dl sine of theta, where theta is the angle that we have talked about, the Gulabi angle. Okay. Pink angle, I meant to say. So dB is proportional to ideal sine of theta upon r square. Right? And of course, the vector dB will be equal to, okay, let me introduce this thing first. So dB becomes equal to, according to the rules of direct proportionality, a constant ideal sine of theta upon r square. This constant I am writing as 1 upon 4 pi into 1 upon mu naught. Okay. Which will become equal to mu naught upon 4 pi. Okay. But there is a certain reason which we'll discuss later on, why I am taking this 1 upon mu naught. So what I get is dB is equal to mu naught 4 pi ideal sine of theta upon r square, where this mu naught upon 4 pi is the permeability of free space, vacuum, something called nothing. Mu naught upon 4 pi is the permeability of free space, how much the free space is permeable to the magnetic entity that we have, and this is, now I am giving the value. The value is 10 to the power of minus 7 Tesla meter per ampere. You can check the unit. It will be Tesla meter. I am not going to prove that to you. Permeability of free space, vacuum, something called nothing, 10 to the power of minus 7 Tesla meter per ampere. This is an assigned value. This value cannot change. At the same time, if it comes to us as what is this 1 upon 4 pi epsilon naught, which has another poetic value 9 to 10 to the power of 9 Newton meter square plus per Coulomb square. What is this? This is an experimentally determined value. So this value is an assigned value. When we put our heads together and we said that this value we are going to take 10 to the power of minus 7 Tesla meter per ampere. Okay. Now let us see, let us try as to what is the value of 1 upon mu naught epsilon naught, combining these two friends together. Epsilon naught, which is the permittivity of free space, and mu naught, which is the permeability of free space. In case, actually this is not mu naught upon 4 pi, but it is mu naught which is the permeability of free space. Okay, so mu naught will be equal to 4 pi into 10 to the power of minus 7 Tesla meter per ampere. You can make that correction. Okay, let me carry on from there. So I am writing 1 upon mu naught into epsilon naught. Writing the value of mu naught 4 pi into 10 to the power of minus 7 into the value of epsilon naught. This will be equal to 4 pi 1 upon 4 pi 9 into 10 to the power of 9. So when I put it here, 1 upon mu naught epsilon naught or 1 upon epsilon naught mu naught, then I put the values from here. Mu naught is equal to 4 pi into 10 to the power of 7 Tesla meter per ampere, doesn't matter, and epsilon naught I am writing 1 upon 4 pi into 9 into 10 to the power of 9. Okay. So what I get, this goes here, jumps there, 4 pi and 4 pi cancel out. 10 to the power of minus 7 will also jump for here as 10 to the power of 7. So the value that I get for 1 upon mu naught epsilon naught is 9 into 10 to the power of 9 to 10 to the power of 7, which will be 9 into 10 to the power of 16. Okay. Now this I can write as 3 into 10 to the power of 8 whole square radian. Of course, when you check the units, then this is meter per second square. So this is equal to c square, where c is 3 into 10 to the power of 8 meter per second, is the speed of light in vacuum in something called nothing in free space. So look here, 1 upon mu naught epsilon naught and c square. So that gives c square into epsilon naught mu naught is equal to 1. Or c I can write as 1 upon under root of mu naught epsilon meter per second. Okay. Now let's come back here. So here we have an interesting thing. Mu naught upon 4 pi, no problem. I, no problem. dl, no problem. R is no problem. The problem is here, sine theta. And sine theta is 0 for theta is equal to 0 or theta is equal to pi. Okay, 180 degrees. So what does that mean? It means that if the real element is as shown by this green arrow, and I extend this line in this direction, also in this direction, so the R in this case is like this. So dl cross R will be equal to dlr sine of 0, and in this case dlr into sine of 180 degrees. So the magnetic field dB over here and the magnetic field dB over here will be equal to 0. That means if I have an element like this or a wire like this, and we want to find out the magnetic field over here or the magnetic field over here, that will be equal to 0. So this is another aspect which is not present in the case of Coulomb's law. Okay. So with that, what is required is that we must compare the Biot-Savart law and the Coulomb's law. And one of the comparisons that I've just made is that both are long range things. They act at long distances. Actually, long and short are very comparative things. And there is a famous story about Akbar's court, that he said, I have drawn a line like this, and I want this line to be smaller without touching it, without removing it. Then one gentleman came and he said that I can make this not only smaller but also longer. So he said that I will draw another line over here and I will draw another line over here. So this is longer than this and this is smaller than this. Okay. This is something very interesting. Okay. Now look here. I have a pen. I have a pen. Okay. I have a pen here. Is it long or it is short? Okay. You can give me your answer. But if I take this pen away from your eyes, away from your eyes, away from your eyes to a very long distance, then this will appear to be smaller. But with the same pen, look here, I am coming to your eyes, and the same pen I am bringing closer to your eyes, closer to your eyes, closer to your eyes. And when it is here, then you can see that this appears to be very big. So in fact, what is it that makes things long or short? It is the angle which is subtended on our eyes. Okay, if that angle is small, then the things are smaller in size, small in size. If the angle that subtends on your eyes is big, okay, and that's why, okay, we have a saying that Aankh oat, pahad oat. Okay, so if you keep something near your eye, you cannot see the big mountain in front of your eyes. Right. So anyway, now both of them are long range, and long range now it compares to the kind of forces that we have, the short range forces, the two nuclear forces, the strong nuclear force and the weak force, and they are extended over to a length of not more than 10 to the power of minus 15 meters. Okay. So I have just given you this thing, that both are long range and both have the proportionality to 1 upon r square, inverse square proportionality. And as a result thereof, both are the members of the same club, and both subscribe to superposition principle. Okay. In both of them, the superposition principle works for the electric field and also for the magnetic field. That is, there is a vector addition, okay, not an algebraic addition. What happened in the case of the potentials, because potential is a scalar, can have positive and negative values. These fields, electric field and the magnetic field, they are fields, they are vectors. So the superposition principle applies as they are vectors. I'll give you more comparisons shortly. So about the various attributes where the Biot-Savart Law is akin to the Coulomb's law, and where the Biot-Savart Law is different from. So I said that both are long range, both are proportional to 1 upon r squared, both subscribe to the superposition principle, and dB is linear in the source ideal. Okay, has a linear dependence on the source. Similarly, just like the electric field has a linear dependence on the source, that is the charge q. Okay. Now there is a difference. Here is the difference that should be borne in mind, and that is the source q for the electric field is scalar, whereas ideal is the source for the magnetic field, and that is a vector. So this is the distinction between the two of them. And the third situation is, the third thing is that we should bear in mind is that the electric field is along R, towards R or opposite to R, but it is along the R, so that we can say that E cap is equal to plus minus R cap. Okay. Whereas dB is perpendicular to R, is in the plane perpendicular to both R and dl. Okay, as I have shown over here, right? Then there is the theta factor, the sine theta factor, and that if the angle between dl and r is 0 degrees or 180 degrees, which is the case for the points p prime and p double prime that I have shown here, the value of the magnetic field will be equal to 0, which I did show here. So with that, I come to an end of introducing and explaining the Biot-Savart Law. The next thing that we'll do is an application of the Biot-Savart Law, and that is as to if I have a current in a loop, in a circular loop, and I go along the axis of that loop, then we would like to find out as to what will be the value of the magnetic field at a distance x from the center of this circular a circle in which a current is flowing, as also we can find out with an extension of that result as to what will be the field at the center of a circular loop. Okay, these two things we'll be doing in the next lecture. Inshallah, I've enjoyed this. Hope you have enjoyed, and let's meet soon.